the product of the refractive index of the first medium and the angle of incidence in it. The product of the refractive index of the first one, the sine of the angle of incidence must be equal to the product of the refractive index of the second one and the sine of the angle of refraction R. And when we make sine I over sine R the subject, we realize that this will also be equal to the refractive index of medium 2 over the refractive index of medium 1. Sine I over sine R is Snell's law, which says that the refractive index as light moves from 1 to 2 is equal to n of 2 absolute refractive index of medium 2 over the absolute refractive index of medium 1. So this is the concept of relative refractive index. Relative refractive index. Yesterday, we also saw that for any two media, the product of its absolute refractive index 1 to 2 and its reverse refractive index 2 to 1, this is equal to what? This is equal to class, this product is equal to 1. Meaning that whenever I'm looking for reverse refractive index must be equal to 1 over absolute refractive index of a material. So the absolute refractive index of glass is 1.5. It means if I'm looking for the reverse refractive index from glass to air, it must be 1 divided by the absolute refractive index of glass, which is from air to glass. And this will be equal to 1 over 1.5. So take note of this. Take note of this. Let's look at when we have three different media, which is joined. Here we were talking about medium 1 and 2. So when we have 3 and even more, so let's pick 3 different media and we can apply the same knowledge to 4, to 5, and so on. So the horizontal lines are basically boundaries or interfaces separating the 3 media. So over here we have medium 1. We have medium 2 and medium 3. Here must be the same as medium 1. So we are actually dealing with 3 media, 1, 2, 3. But here it is like the light is incidented in air, water, glass, and it is emerging into air. The light is finally coming out from the air. Okay. Now the refractive index of this is N1, N2, N3, back to N1. So let's disregard this. We incident light in medium 1 So let's incident light in medium 1. Kezia, are you there?
Yes, sir.
Kezia, how would the light is moving from medium 1 into medium 2? Now this is the arrangement of the material is in this way. The refractive index of 1 is less than the refractive index of 2. And the refractive index of 2 is also less than the refractive index of 3. So in this case, Kezia, how will the light bend? Will it bend as it moves from 1 to 2? Will it bend towards the normal or away from the normal? Kezia?
Please towards the normal.
Why? Kezia, why?
Because the refractive index of N2 is greater than N1.
Thank you. So it will bend towards the normal and enter into medium 2. This is the normal. The bending of light actually takes place at the boundary. So when the light gets to the boundary, then it will bend. So this is N1, another normal, N2. This is refracted ray, point of incidence. The light is also passing through medium 3. How will it bend? In medium 3, will the light bend away from the normal or towards the normal, class? Kezia again.
Please towards the normal.
Why?
Because N3 is greater than N2.
Thank you. Class, I'm sure you are all following. Lamp and the rest of you. Ohima.
Yes, sir.
So this is also the point of another refracted ray. Let's have another normal at the third boundary. Now when the ray is coming out of medium 3 to back to the medium 1 here, how will it bend? Will it bend towards the normal or away from the normal? Anybody, will it bend away from the normal or towards the normal? Oh, let's not waste time.
Away from the normal.
So it will bend away from the normal. Because among all the three, medium 1 is the least dense medium. So it will bend away from the normal. So we call this as the emergent ray, the ray emerging from the media. Emergent ray. So this is the incident ray. The ray within the media are refracted. and this is the emergent ray. So refraction would occur at boundary 1, boundary A, another boundary B, and C. Please note that refraction occurs at the boundaries. Okay. So within the same, when it hits the boundary separating the two media, then the light will be refracted. Okay. So we are looking at when we've looked at when we have 2. Okay, and also considering when we have 3. So let's go through it. I want to drop attendance. Okay, so give me a minute. Okay, so back to you. Now I want to consider the refraction occurring at each boundary or at each interface. Let's consider that when the light enters into medium 2, the angle of refraction, this is R1. Then when it enters into medium 3, the angle of refraction here, this is R2. And the angle of emergence is R3. So considering the boundary A, this boundary, if we want to consider the deviation or the refraction of light, Snell's law, refractive index as light moves from medium 1 to medium 2, this is equal to sine of the angle of incidence, which is I, over sine of the angle of refraction, which is sine R1. Class, are you okay with this? Are we okay here?
Yes, sir.
Yes, sir. Yes, sir.
Okay, so let's also consider refraction of light at boundary B. Refraction at boundary B. Note that I said refraction occurs at the boundaries. Now, so if we are considering the refractive index as light moves from medium 2 to 3, 2 to 3. Class, what is in medium at the second boundary A? What do you think will be the angle of incidence? What will be the angle of incidence here? this angle. Look at it carefully and tell me the angle of incidence within medium 2.
R1.
Why?
Alternate angles.
Let's
The
clap for
R1
her.
is
Save your English for another lesson. You are absolutely right. Okay, so it will be R1 because these two angles alternate. So sine R1 over sine the angle of refraction in medium 3 is R2. So let's also look at refraction of light at boundary C. So refractive index as light moves from medium 3 back to medium 1. This will be sine of, yes, what will be the angle of incidence here? What will be the angle of incidence there in medium 3? Oh, let's not waste time. What is the angle of incidence there? Nana Hebron.
That is R2.
Exactly. Because of the same reason, alternating angles are equal over sine R3. Okay. So when you have 3, 4, 5, you consider it bit by bit. Now, class, note an important point. An important point we are going to apply. Refraction of light. In refraction of light in parallel boundary of light at parallel boundary or interface, the angle of incidence I is always equal to the angle of emergence R3. What I'm saying is that whenever you have two boundaries and the boundaries are parallel to one another, look at this boundary. 1, 2, 3. They are all parallel to one another. So whether you have two media, 3, 4, 5, and the refraction of light along parallel boundary, the angle of incidence is always equal to the angle of emergence. So if supposing the angle of incidence is 30 degrees, when the light is coming out through the same medium, 1, 1, that the emerging ray or the angle of emergence, please, this R3 is what we are calling as angle of emergence. Don't forget, I said that the ray is known as emergent ray. So the angle there is also known as angle of emergence. So for refraction of light along parallel plane, angle of incidence. Oh, Techno F1, please. I think it will be a network problem. Okay, can you rejoin? Can you please rejoin? So for refraction of light along a parallel boundary or plane, angle of incidence is always equal to angle of emergence. Okay, take note of that. And this thing you prove it in underlight practicals. You a simple experiment to show that angle of incidence is equal to angle of emergence. So if I is equal to R3 due to this reason, then let's multiply the refractive indices of all of them and see something. So refractive index from 1 to 2 times the refractive index from 2 to 3 times the refractive index. Please, is it a general problem?
No, sir.
So can you please go off and rejoin? Okay, leave the meeting. If you still have that challenge, can you leave the meeting and rejoin? I'm sure it's a network problem from your end. Besides, I'm also recording. So we are multiplying all the refractive indices at the various boundaries. So times the refractive index from 3 back to 1. This must be equal to, for the first one, 1 to 2, we had sine I over sine R1 times sine R1 over sine R2 times the last one, sine R2 over sine R3. Now, you realize that this will cancel this. This would also cancel this. And because I is equal to R3, sine I would also cancel sine R3 because they are equal. Therefore, the refractive index from 1 to 2 times the refractive index from 2 to 3 times the refractive index from 3 back to 1, this product is equal to what? Class, this product is equal to what?
1.
Is equal to 1. So for 3 composite media, this is the product of their refractive indices in that orderly manner. The clue to this is that the 3 media must be such that the refractive index of 1 must be less than the refractive index of 2, and this must also be less than refractive index of 3. If you miss them, they will not work. It can be, so the media in question can be from air to water times refractive index from water to glass times the refractive index from glass back to air. You see, air is less dense. Okay, the less dense one, followed by water, followed by glass. If we miss them, the rule will not work. You can't apply this product rule of their refractive indices. Refractive indices. So for this to work, the refractive index of the first one must be less than the second one, must be less than the third one, or the third one must be greater than second one. The second one must also be greater than the first one. You can't mix them. If you have 4, the same rule. If you have 4 media, the same rule would also work. I'm not going to draw, but assuming we have 4 media, then it means refractive index from 1 to 2 times refractive index from 2 to 3 times the refractive index from 3 to 4 times the refractive index from 4 back to 1. This product must be equal to 1. 5, the same thing. And don't forget, we saw it for 2. For any 2 composites, the refractive index from 1 to 2 times the refractive index from 2 to 1 must be equal to 1. This is the rule for composite media. Please, is there any question? Is there any question?
No, sir.
We are going to apply this in answering a question. So if you are writing, quickly do the writing whilst I look out for the questioning. Okay, are we ready? Are we ready? Class, are you ready?
Yes, sir.
Yes, sir.
Now, given that the refractive index from 1 to 2 is 4/3, and the refractive index from 2 to 3 is 3/2. Find the refractive index from 1 to 3. Given that the refractive index from 1 to 2 is 4/3. 1 to 2 is absolute refractive index. And then the refractive index from 2 to 3 is 3/2. Find the refractive index from 1 to 3. So this is the problem. How do we solve such a question? So how many different media do we have here?
Say please 3.
We have 3 different media here. Okay. So if we have 3 of them, then it means that the refractive index as light moves from 1 to 2 times the refractive index as light moves from 2 to 3 times the refractive index as light moves from 3 back to 1. This product is equal to what?
Sir, 1.
1.
1. Very, very important points. So if it is 4, it will be 1, 5, and so on and so forth. So we are looking for 1 to 3, but we don't have 1 to 3. Do we have the refractive index from 1 to 2? Yes, 4. So this is 4 over 3 times. Do we have from 2 to 3? Yes, 3 over 2 times what? We don't have what the question demands, but we have the refractive index. This is 3 to 1. So find from this, let's determine the refractive index from 3 to 1. Help me do that. What will be the Nana from?
Sir, please, I go half.
So let's see if that's half. This and this will cancel. 2 will go into itself 1. 2 will go into 4, 2. So we basically have from 3 to 1 times 2, which is equal to 1. We divide through by 2, and we have the refractive index from 3 to 1 to be equal to half. This is the first step. The second step is that we've also learned that for any two composite media, the refractive index from 1 to 3 times its reverse refractive index 3 to 1, this product is also equal to 1. Now we have from 3 to 1, we can find from 1 to 3. Therefore, the refractive index from 1 to 3 would be equal to 1 divided by the refractive index from 3 to 1. And this is 1 over half. And what is 1 over half? Class, what is 1 over half?
Sir, please, 2.
So this is 2. So the answer for the question is 2. Please, are we okay?
Yes, sir.
All right. Another question for you to try. This time you will do it, after which I would discuss it with you. So please listen attentively and then put that down. Refractive index of glass with respect to water. Refractive index of glass with respect to water is 9 over 8. Refractive index of glass with respect to water is 9 over 8. Refractive index of glass with respect to air is 3 over 2. Find the refractive index of water with respect to air. Refractive index of glass with respect to water is 9 over 8. And the refractive index of glass with respect to air is 3 over 2. Find the refractive index of water with respect to air. Start work. Whose hand is up? Hefron, have you finished?
Sir, please, was a mistake.
Okay. You have 3 minutes more. One minute more. 1 minute. Okay. I think our time is up. Our time is up. Okay, let's see what you had. Everyone, what's your answer?
Sir, please, I'm still solving it.
Okay. Zara, what's your answer?
Please, I had 16 on 27.
16 on 27. Okay. We shall see. More views. More views. Evelyn, what's your answer?
Sir, please, I had 3/4.
We shall see. Ohima,
Sir, please, I had 1.33.
leave your answer in fraction. Give me your answer in fraction. Grace.
Sir, please.
Mhm.
Sir, please, I had 16 on 27.
We shall see. Keziah.
Please, I had 4 on 3.
And finally, Rabiatu. Rabiatu.
Sir, please, my line was breaking, so I didn't get the question well.
Yo. Ohima, I asked you to have your answer in fraction.
Sir,
What?
please.
Mhm.
18/24.
Oh, you can still break it down.
4/3.
4/3. We shall see. Okay, so what is my take? We are told the refractive index of glass with respect to water. Glass with respect to last time I told you that the with respect to simply means that is the first medium. So the first medium is water and it is entering into glass. And the refractive index is 9/8. Then the refractive index of glass with respect to air is 3/2. So this is absolute refractive index of glass, which is 3/2. It means that this one is relative refractive index of water and glass. And this is the absolute refractive index of glass because the light is from air. And then we are asked to find the refractive index of water with respect to air. So we are to find the absolute refractive index of water. So it means that it must be in increasing refractive indices. We'll only start with air. So refractive index of air must be less than refractive index of water and must also be less than the refractive index of glass. In that case, we can say that the product of the refractive index of this air to water times the refractive index of water to glass times the refractive index of glass back to air, this product must be equal to 1. We are looking for the first one, air to water. Do we have from water to glass? Yes, 9/8. Do we have from glass to air? We don't have glass to air directly, but we know air to glass. And we also know that the refractive index from glass to air would be equal to 1 divided by the refractive index from air to glass. Therefore, we can find what we don't have, and this will be equal to 1/3/2, which is 2/3. So we substitute that here. 2/3 is equal to 1. Therefore, 3 goes into 9, 3. 2 would go into 8, 4. Okay, so the refractive index from air to water or of water with respect to air will be equal to 1 divided by 3/4. And 1 divided by 3/4 is equal to 4/3. Let's change 4/3 to decimal. Help me change 4/3 to decimal. Oh, let's hurry up.
1.333.
You see, yesterday I told you that the refractive index of water is this, the absolute refractive index. So your answer must actually be 4/3. Ladies and gentlemen, is it understood? Hey, are you people there?
Yes, sir.
All right. Put this question down for trial. So this is how to apply this concept in solving problems, okay? I have this question which I want you to try. A monochromatic light, monochromatic light is just light of one color. A monochromatic light beam of frequency 6.0 times 10 exponent 14. Please give me a minute, I'm coming here. I'll be with you. So a monochromatic light of frequency 6.0 times 10 exponent 14 Hertz, 6.0 times 10 exponent 14 Hertz, process from air into a transparent material, process from air into a transparent material where its wavelength is measured to be 300 nanometer. It crosses from air into a transparent material where its wavelength is measured to be 300. So lambda in the transparent medium is 300 nanometer. What is the index of refraction of the transparent material or the material? What is the index of refraction of the material? Class, I'm giving you 5 minutes. It's 7:15. 7:15. So at exactly 7:20, I'll come your way. Good luck. Please, I said you can discuss. You can discuss on the platform, and I love it that way. All right, all the best. I'll return to you after 5 minutes time. Time is up. Your time is up. Yes, can I get your answers? Can I get your answers? What did you get as the index of refraction of the material? Any one of you can start, or you are just sharing what you had with us. Yes. Hey, everybody is quiet. Hey, can you hear me?
Yes, sir.
Talk to me. Share what you had with me. Hey, everybody is quiet. So none of you was able to finish. Hello.
Hi.
I said none of you was able to finish. If you finished, share what you got with me. Amazing. UP, are you there?
Yes, sir.
I'm surprised you are all quiet. The instruction is straightforward. If you were able to finish, share with me whatever you were able to get. That's all. And I'm not calling individual names. Any one of you can do that. Hey, class, you are disappointing me. I talked about this some time ago. Class, whenever you are learning, let your class be interactive. Even when you've managed to get rubbish, share. You don't only always learn and decide to be quiet and then be listening to the teacher. I gave you some time to solve this. So whatever you are able to get, share with me. And I'm surprised everybody is quiet. You joined the class with the other students and you saw how interactive they were. Okay. When you are quiet during lessons, it develops to that timidity. You'll be timid, be vocal. And I have given you the chance to just share whatever you got with me. Meaning, I don't want you to be called before. Feel free, let's interact. That is a better way of learning than the old traditional way, hey, no, that is sometimes military. I don't like that. I'm surprised for 5 minutes, none of you want to even talk. Not disappointing me. I'm totally disappointed because I thought you have overcome this, only to realize that it is still there. I won't call anybody. If you won't share, keep it. So listen. A monochromatic light of frequency 6.0. So the frequency is 6.0 times 10 exponent 14 hertz. Passes from air into a transparent medium where its wavelength is measured to be. So the wavelength, it passes from air into a transparent medium where its wavelength is measured to be 300 nanometer. What is the index of refraction? So we learned about refractive index in several forms. Refractive index of a medium can be sine I over sine R. Refractive index, absolute refractive index, is C over V. And refractive index can also be wavelength in air over wavelength of light in a medium. Looking at information provided, the first one is out of the context. We cannot use this because we don't have anything angles. So we can't use the first one to solve the problem. Can we use the second one? Let's see. The second one is about speed of light in air against speed of light in a medium. Yes, we know the speed of light in air is a constant, 3.0 times 10 exponent 8 meter per second. What about speed of light in a medium, V? We can find this using V is equal to F times lambda. Where V is equal to speed of light or velocity of light in the medium. F is frequency of light, and lambda is wavelength of light in a medium. So we can find V to be frequency, which is 6.0 times 10 exponent 14 times wavelength of light in a medium. And that is what was provided, where its wavelength is measured to be 300 nano. Nano is 10 exponent negative 9. So we have 18. This is 6 times 10 exponent 14 times 3 times 10 exponent minus 7. So we have 6 times 3, 18, times 14 minus 7. This is 7. When we shift the decimal place 1, we have 1.8 times 10 exponent 8 meter per second. So this will be the velocity of light in a transparent medium. So once we have V in the medium,
Sir,
hello?
sir, please, the V, the first one, the 300 nanometers, you wrote 300 times 10 exponent negative 9. But the second one, you wrote 3 times 10 exponent negative 7.
It's not wrong. This is what I did. See, 300 is 3 times 10 exponent 2, isn't it? Isn't it?
Yes, sir.
So times 10 exponent negative 9, then the nano. So we have 10 exponent 2 minus 9. And what is 2 minus 9?
Minus 7.
So that's what you have here.
Okay, thank you.
Welcome. And this is what I like. Ask questions. If you don't understand something, ask. You don't keep it. Mama Medjamumu. Therefore, the refractive index will be equal to C. C, speed of light in air is 3 times 10 exponent 8 divided by speed of light in the medium, which is 1.8 times 10 exponent 8. This and this will cancel out. What is 3 divided by 1.8, class?
Sir, please, 1.667.
1.667. So approximately 1.67. That's the refractive index. Then let's use the third formula. The third formula says that the refractive index, wavelength of light in air divided by wavelength of light in the medium. Do we have the wavelength of light in air? No. But we have the wavelength of light in a medium, the denominator. How do we get wavelength of light in air? We know velocity of light in air, C, for velocity of light is basically equal to F times lambda. C is actually velocity of light in air, meaning this is equal to frequency of light times the wavelength of light in air, since this is air. I told you yesterday that frequency of light does not change from one medium into another medium. So for frequency of light, it's a constant. Therefore, wavelength of light in air is equal to speed of light in air divided by the constant frequency of light. What is the speed of light in air? 3 times 10 exponent 8 divided by frequency of light, which is 6 times 10 exponent 14. This is half. 3 over 2. This is half, which is also the same as 0.5. So we have 0.5 times 10 exponent. What is 8 minus 14?
-6.
So minus 6. Now I want to express this in standard form. So I have 0.5 and I will shift it till I have, so I'll shift it to the right. 1, 2, 3. So I have 500 times 10 to the power negative 3, also times 10 to the power negative 6. This negative 3 is here because I shifted the position of the decimal place to the right 3 times, and that's how come I got 500. So when I move it one, I have 5. When I move it twice, I have 50. When I move it thrice, I have 500, and that's why I have it here. All right. So it means this is equal to 500 10 to the power -9 nano. 10 to the power -9 is nano. So nanometer. This is wavelength of light in air. Therefore, the refractive index will be equal to 500 nanometer divided by the wavelength of light in a medium, which is 300 nanometer. Class, what is 5 divided by 3? What is 5?
1.67.
So 1.67. The value is the same, whichever way you look at it. So this is, don't forget, it is not the whole, I use these two formula to solve the same question. So I've given you two different solutions to the problem. Okay, please, this one ends here. This one ends here. And who was able to get 1.67? Who had 1.67? None of you was able to get 1.67. Okay. So if you are copying, please do that quickly. Can we move on, or you are still writing?
Sir, please, I'm writing.
Okay. When you finish, please tell me. Ohima, are you there?
Yes, sir.
Yes, sir, you don't talk. Ohima, you don't talk.
Side chick. Oh no.
Grace. Grace, mute yourself. Can we continue?
Yes, sir.
Okay. The next sub area I want us to look at is total internal reflection. Total internal reflection. Total internal reflection, in short, TIR. This is actually reflection of light under refraction. You see, the concept of total internal reflection is under the topic refraction. Okay, it's under the topic refraction. So I will describe it as reflection of light under refraction. So reflection under refraction. And it has a lot of natural applications, natural and then even artificial applications. Before I define the concept of total internal reflection, let me give you diagram explanation. When you understand it well, you can be able to even explain it yourself. So we have light traveling from a more dense medium into a less dense medium. So practically, light can travel from glass to air, water to air, okay, oil to air. The light must come from a more dense medium and then emerge, okay, emerge into a less dense medium. So the horizontal line, of course, is the boundary between the two media. So since we are going to draw a ray, we need the normal. This is because all angular measurements are determined from the normal. So when we incident light into this, the light is coming from the more dense medium. When it gets to the boundary, how would the light be refracted? How would the light be refracted at the boundary? I'm listening to you. Hey, I think my question is clear. The light is coming from